Hello. Today we're going to talk a little bit more about some operational properties for Laplace transforms. We have some translations that occur along the x-axis as well as on the t-axis. So pretty quickly, using the definition of the Laplace transform is going to be way too cumbersome, right? So we're going to have to figure out how we can notice patterns, how we can use the table to really help us, okay? So it turns out that if we have an exponential multiplier with a function and we're trying to take the Laplace transform of it, what's going to happen is, I'm showing you down here, we take the Laplace of e to the at f of t. In the s world, that's going to show up as a shift and an s minus a, okay? So a can be any real number, positive or negative. Of course, if a is negative, then that becomes s minus a negative a, which would be s plus a, okay? We're going to first talk about how we can handle the Laplace and the inverse Laplace transforms of these. And then we're going to learn about the second translation theorem. And then finally, we'll work through some examples using these, okay? So here's what I do for myself, and this just kind of helps me as I evaluate Laplace transforms. So I see that I have the Laplace of some e to the at f of t. So I go ahead and I rewrite that as Laplace of f of t, but then I have an evaluation bar, this vertical bar on the outside of the curly brackets, and at the base of it, I tell myself that after I find big F of s, I need to replace s with s minus a. And that gets me to the big F of s minus a, okay? And it just, for me, it keeps things a little bit clearer, all right? And on the flip side, if we want to take the inverse Laplace transform for this first translation theorem, so then let's say that we're taking Laplace inverse of big F of s minus a. What we can do is rewrite big F of s minus a as big F of s with an evaluation bar saying that s would go to s minus a. And what that evaluation bar turns into after we take the Laplace inverse is that e to the at on the outside of an f of t. Okay, so let's work on a few examples and see how we apply this. This first example, we're being told to find either big F of s or little f of t as indicated. This first one, we have the Laplace of t squared e to the 3t. So that exponential function is in there. Right away, I'm going to rewrite this based on the idea that a is 3. Okay, so this becomes the Laplace of t squared. Outside of the curly brackets, I evaluate s going to s minus 3. Okay, well, the Laplace transform of t squared, that's the one that's going to give us a 2 factorial over an s squared. And then that is going to be evaluated where s goes to s minus 3. And so we finally do that evaluation, and our final answer will be 2 over, in quantity, s minus 3 all squared. Okay, so this Laplace of t squared, just to remind you, we have this Laplace transform table that's in the back of the book. I was just using the third one there. And I'm going to reference this table several times throughout this lecture, and that's why I have it open so that we can learn how to use it together. All right, next example, we want the Laplace of e to the minus 3t sine of 2t. So here, I'm noticing that a is equal to minus 3. So the opposite sign of the previous one. I'm going to rewrite this so that I focus on the Laplace of sine of 2t, close the curly brackets, and we're going to evaluate whatever we get we're going to change s to s plus 3. Okay, well, the Laplace of sine of 2t is 2 over s squared plus 4, but that needs to be evaluated where we take s to s plus 3. So we finally do that, and we get an answer of 2 over, in quantity, s plus 3 all squared, with a plus 4 on the outside. And that's our final answer. And so again, going back to our table of Laplace transforms, If I scroll down a little bit, I get to number 7, and that shows me the Laplace of sine of kt. And then in the next page, we're going to look at some Laplace inverse problems. I really focus on one. It's a bit long. So in this problem, we're taking Laplace inverse of 3s minus 2 all over s squared plus 3s plus 1. Well, you know what? I had meant to replace that, actually. I'm sorry. Let me cross this out. I want this to be Laplace inverse of 3s minus 2 all over s squared plus 3s plus 3. Sorry about that. That was a typo that I had meant to go back and fix. All right. So normally what I would do is, well, let's look at the table and see, kind of get an idea. If I'm looking at the table and I'm looking at the right side column for functions in S that look similar to what I have, the 3s minus 2 all over s squared plus 3s plus 3. And I'm focusing on the denominators, and right now I don't see any quadratics with all three terms in the denominators. And so I'm thinking, oh, maybe 18 or 19 is going to help me. So in 18 and 19, it looks like it's kind of weird, but there's an s minus a all squared and then plus an extra number. That kind of reminds me of what would happen if I was to complete the square on the s squared plus 3s plus 3. Because s squared plus 3s plus 3 doesn't factor at all. So I'm literally kind of stuck unless I figure out, like, what do I need to do? So the denominator doesn't factor. If it did factor, this would be like what we did in the previous section. So we complete the square. Okay, so s squared plus 3s plus 3 is equal to s squared plus 3s plus something minus that something plus 3. So I'm going to add and take away the plus c term that I need. To figure out what we need to add and take away, we look at the b coefficient, which is 3. We take 3 divided by 2 and square it. That is 9/4. So we're going to add in a 9/4 and take away a 9/4. And then we simplify that. The s squared plus 3s plus 9/4, that is going to factor as s plus 3 halves all squared. The goal is to get a perfect square trinomial. And then we have the plus 3 and the minus 9/4. So minus 9 over 4 plus 12 over 4, that's going to give us plus 3 over 4. Okay, so we are actually looking at the Laplace inverse of 3s minus 2 over, in quantity, s plus 3 halves, all squared, plus 3/4. Okay, now another issue is the numerator has too much stuff. And what I mean by that is, let's look at the Laplace transform table, because now we have a denominator that looks like 18 and 19. But notice the numerator, we have 3s minus 2, and the options here are k and s minus a. And we have a little bit too much going on, but I want you to notice for number 19, for the e to the at cosine of kt, in the denominator is that s minus a, and that also shows up in the numerator. So the shift has to show up in both places where s shows up, okay? So I think what we need to do is play around with our numerator. 3s minus 2, somehow I need that shift of the plus 3 halves with my s. And here's how I do it. I get 3 And then I'm going to put some parentheses and write s plus 3 halves minus 3 halves, and then close the parentheses. Those are almost equal. I still need the minus 2 on the outside. Okay, so I haven't done anything except add in a funny looking 0 in order to get what I need for this problem. Now I'm going to distribute the 3 across to the two terms, where one of the terms is s plus 3 halves and the second term is minus 3 halves. So this then becomes 3 times s plus 3 halves, and then minus 9 halves, and then the minus 2. Minus 2 can be rewritten as minus 4 over 2, so this becomes 3 times s plus 3 halves minus 13 halves. Okay, so really what we're looking at is the Laplace inverse of 3 times s plus 3 halves minus 13 halves all over in quantity s plus 3 halves all squared plus 3/4. Okay, now I can split up the fractions and then see what kind of algebra I have left to do. So when I split up the fractions, I'm using linearity of the Laplace inverse transform to rewrite it as 3 times the Laplace inverse of s plus 3 halves all over s plus 3 halves all squared plus 3/4 minus 13 halves times the Laplace inverse of 1 over s plus 3 halves all squared plus 3/4. Okay, so now this is almost how I want it. When I'm looking at the first one, the Laplace inverse of s plus 3 halves over the s plus 3 halves squared plus 3/4, this looks good. Okay, we have a is equal to minus 3 halves, and k is equal to the square root of 3 over 2. Okay, but the second one over here, the numerator is not quite right. I have that k is equal to the square root of 3 over 2, but I need k to be in the numerator, okay? So what I have to do is multiply this whole thing by a square root 3 over 2 over a square root 3 over 2. I'm going to go back to the table to show you why. When we deal with 18, e to the at sine of kt, we're looking at starting, we're working backwards. So we should have a k in the numerator, and in the denominator, we should have a plus k squared. That's where I'm getting my k values from, okay? And so we've got to focus on fixing that numerator, and that's what we're going to do. So in the next line, I'm going to rewrite this. I have 3, the Laplace inverse of s plus 3 halves all over the s plus 3 halves all squared plus the 3/4. This I can rewrite as the Laplace inverse of s over s squared plus 3/4 evaluated where s went to s plus 3 halves. So we know that's going to give us our exponential multiplier in the little t world. Then we have the minus 13 halves divided by the square root of 3 over 2. So that's where I'm bringing this square root 3 over 2 that was in the denominator, bringing it outside. And then times the Laplace inverse of the square root of 3 over 2 all over s plus 3 over 2 all squared plus 3/4. I'm really trying to take each of these kind of step by step here. All right, the first one is perfect. I have 3. The shift tells me I have an exponential multiplier of e to the minus 3t over 2. And then the s over s squared plus 3/4, that's going to give me a cosine of k, t, and k was the square root of 3 over 2. And then that's times t. Minus, if I take 3 halves and divide it by this root 3 over 2, I end up with 13 over root 3. And then I can rewrite my Laplace inverse as being the Laplace inverse of root 3 over 2 over s squared plus 3/4, where s came from the s plus 3/2. One more rewrite and then we're done. So the first one's already done. That's 3e to the minus 3t over 2 cosine of root 3 over 2t minus 13 over the square root of 3. We have the exponential multiplier coming in again from that shift. That gives us the e to the minus 3t over 2. And then the Laplace inverse is going to be a sine of k, which is root 3 over 2 times t. And that's our final answer. So that was quite a bit of work, and it may have been some algebra that looks kind of foreign or way, way, way back in time for you. So definitely review completing the square, multiplying by funny looking ones, and adding funny looking zeros. Those skills are all going to help you a lot in this section. All right. The next part of this section talks about the translation on the t-axis. So we just dealt with the translation on the s-axis because it was a shift on the s-axis. And so we should expect that when it's translation on the t-axis, that means a shift on the t-axis. But before we can talk about it, we need to learn about this unit step function. So we have a piecewise function which reflects a physical system that is off up until a certain time and then on from that point forward, or vice versa, okay? But this is the most general unit step function. We use a capital cursive style U of t minus a, and it is equal to this piecewise function where the first piece is 0 when t goes from 0 to a, and that's showing down here on the graph. And then at t equals a, this unit step function is now equal to 1. Okay? And that's really all that it does. However, we can use the unit step function to be a multiplier of another function. And so then the unit step function just acts like a switch. It turns functions on and off. Okay? So if we have a piecewise function f of t, we would like to use the unit step function to rewrite the piecewise function as a sum of pieces. And the unit step function will allow us to do that. It will be used to signal when to turn off a piece and when to turn on a new piece of the piecewise functions. Once we can do that, then we can take the Laplace transform of a piecewise defined function. Because the unit step function will provide a shift horizontally in the f of t world, we will expect to see an exponential function multiplier in the Laplace world. And that is exactly what's going to happen. And it's the exact opposite of what we just saw in the first translation theorem. So there's some similarities going on here. But first, we need to practice writing piecewise functions in terms of unit step functions. Okay? A piecewise function is always a function that has pieces that are only defined for certain intervals of the domain. So to write one as a sum of functions, we're going to use that unit step function. Here's an example of how I would do this. I'm going to really walk through this step by step, and you can read it, but I'll also state it. This is kind of a big doozy of a piecewise function, and I have f of t in there, and it should be, I have f of x, and it should be f of t in there. Sorry about that. All right, f of t is a 4-piece function. The first piece is t when t goes from 0 to 2. The second piece is 1 when t goes from 2 to 4. The third piece is 0 when t goes from 4 to 5. And the fourth piece is cosine of t when t is greater than or equal to 5. Now I want to show you something here, kind of what was going on. This is going to be a rather rough sketch, but let's see. And 1, 2, 3, 4, 5. Okay, so what's happening here is from 0 to 2, we have the function t. F of t equals t goes through the origin, it goes through 1, 1, and it goes through 2, 2. So it's a straight slanted line with a slope of 1, okay? But at t equals 2, it shuts off, and then a new function starts at 2. It's the function f of t equals 1, which is a horizontal line, and it looks like it goes from 2 to 4, okay? Then at 4, the function is equal to 0. So we just have a horizontal line along the t-axis. But then at 5, at t equals 5, the function picks up again, and it acts like a cosine function. And so this will not be totally accurate because I'm just going to kind of draw a cosine wave on there. But this is the idea of what's going on. So for different points in time, this function has a different shape to it. And I want to be able to write that picture that I just drew as one function. So to start with, f of t is equal to t, right? We drew that. We see it in the first row of f of t. But then that's going to have to shut off at t equals 2. To do this, we have to subtract. Subtract always means turn off. So we have to subtract t at the time t equals 2. When we do this, here's what we're doing. We're saying minus t times the unit step function of t minus 2. The u of t minus 2 literally tells the system only at t equals 2 will we do this shut off of t, okay? Then our function is stating that it's equal to t. Okay, I already said that. Okay, so next our function is stating that it is equal to t right up until t equals 2. So that's what we have written so far. Now it needs to get turned on again. Okay, addition always means turning on. And when it turns on, it's got to turn on as the function 1. But this has to happen at t equals 2. And then it needs to get shut off again at t equals 4. Okay? So this means our function, we're going to have a plus 1 times u of t minus 2. So that's turning the system on and running it like the second piece of the function. But then we're going to turn it off. So we have minus 1 times u of t minus 4. So that literally gives us this small slice on our graph. All right, the third piece says that we are going to do that's kind of weird because the system's already off at t equals 4, and so the function's already at 0, so we don't have to add or subtract anything to indicate it, but here's what it would look like. You would be turning on the system as a 0 at t equals 4, so you have the u of t minus 4 to get you to 4, and then we would turn it off again, so we'd turn off 0, u of t minus 5. But that combination of two things, even 0 times anything is 0, even 0 times the step function. So this whole combination is just 0. So I don't have to write it in to my function. However, we do have to turn the system on again at t equals 5, and then it's going to stay on forever. And it turns on as a cosine function. So here's what that looks like. Plus cosine of t, u of t minus 5. And that is it. That is f of t. Here's our final product, or sum, I should say. F of t is t plus, I did some math here. Hold on. So up above, where I had the minus t, u of t minus 2, and then the plus 1, u of t minus 2, those have a common u of t minus 2 in them. And if you factor it out, you leave behind a 1 minus t. So that's what this second piece is right here. The u of t minus 4, there was only one piece. It was a minus 1 u of t minus 4, so we leave it alone. And then the cosine of t with the u of t minus 5, there's only the 1. Okay? So that's it. That's the idea. I don't want you to think that it's any more difficult than that, because it really isn't. And I would not focus on memorizing forms that are shown in the book, because honestly, it tends to just make it even more difficult to understand what you're doing. If you think of this as just a system of turning things on and off, then there's no problem. You can always simplify your function when you're done. So let's look at these examples. We want to write each function in terms of unit step functions. This first one, f of t, has three pieces. The first piece is 1 when t goes from 0 to 4. The second piece is 0 when t goes from 4 to 5. And the third piece is 1 when t is greater than or equal to 5. So we start off with what the first piece is. F of t is equal to 1. And that's at t equals 0, so we don't need a unit step function to get there. But we do need a unit step function in order to turn it off at time equals 4. So we have minus 1 u of t minus 4. Okay. Then, and I'm going to write this even though in the next line I'll stop writing it, the second piece is 0. So we write plus 0, and that turns on at time equals 4. So we need u of t minus 4 to turn it on at the right place. But then we'll turn it off. We're going to turn off 0 at t minus 5. So we have 0 times u of t minus 5. And then we turn the system on again. The third piece is 1. So we have plus 1. And it turns on at t equals 5. So we have u of t minus 5 to get us there. And that stays on forever. So when we rewrite this, the 0 terms go away and we're left with 1 minus u of t minus 4 plus u of t minus 5. And that's it. Oftentimes, the simplified form of f of t doesn't necessarily give us information about what the piecewise function looked like because we lose some pieces, like the zeros. Okay? All right, the second one, we are given f of t is equal to 0 to start with, while t goes from 0 to 3 pi over 2. And the second piece is sine of t, where t is greater than or equal to 3 pi over 2. Okay, so we start off with the first piece. F of t is equal to 0. I always just write it, even if I know I'm going to stop writing it when I rewrite. Okay, so my first piece is 0, and it's 0 until time equals 3 pi over 2. So I shut it off. That's minus 0 at t equals 3 pi over 2. So it's u of t minus 3 pi over 2. All right, plus I'm going to turn the system on again. And when I turn it on, it's a sine of t at 3 pi over 2. So I need a u of t minus 3 pi over 2. And then when I rewrite this, all that I have here, the only non-zero term is sine of t, u of t minus 3 pi over 2. Okay? The next piece has three pieces. None of them are zeros, which is good. So we can kind of see another one fully formed. All right, three pieces. The first piece is t. So f of t is equal to t. And that's from t equals 0 to t equals 2. And then it shuts off at 2. So we need minus t, u of t minus 2, in order to take care of the turning on and then the turning off. We turn on 2, so that's plus 2 at t equals 2. So we get a u of t minus 2. And then we're going to turn off the 2, so minus 2 at t equals 5. So it's a u of t minus 5. Last piece, we're going to turn on a 7 minus t, so put parentheses around that. We'll do that at t equals 5, so we need a u of t minus 5. And that's not going to stay on forever. That's going to shut off at 7. So then we have a minus, in parentheses, 7 minus t times u of t minus 7. Okay, now I do want to simplify this because there are some like terms in here. For example, the terms that both have u of t minus 2, and then the terms that both have u of t minus 5. We need to combine those. So the first piece is t. The second piece we'll do plus, factor out the u of t minus 2. That leaves behind a 2 minus t, and then we have our u of t minus 2. And then for the u of t minus 5, so we factor that out, and when I combine everything, I have a plus 7 and a minus 2, so that's a 5, and I have a minus t, and that's times u of t minus 5. And then lastly, I'm going to distribute that minus sign in so that I'm looking at a plus, in parentheses, t minus 7, and then a u of t minus 7. And that's as simple as it gets. Okay? All right, so that's the unit step function. Now we can actually talk about the second translation theorem. First, we got to get to know the tool, then we can use the tool. So if we're trying to take the Laplace transform of a function f that has a shift, t minus a in it, and it's multiplied by a unit step function of t minus a, then that u of t minus a is going to introduce an exponential multiplier in the s world. Okay? I have to admit that this form that I'm showing you in this first line is not my favorite form to use because it requires us to use algebra to get f of t into an f of t minus a form. And that doesn't always go so well for everybody. And I find it's nice if we have something easier to use, then let's use the easier thing. And so that's what I do. I always use L of g of t, where g of t is just like your f of t. It's just like, in other words, of a function of t with no shift in it. So the Laplace of g of t times a u of t minus a, what that's going to do, I really should have checked all my typos a little bit better. It's going to give us an exponential e to the minus as on the outside. And then notice I haven't taken care of my Laplace transform yet, but I took care of the u. The u of t minus a introduces an e to the minus as, and then we can focus on taking the Laplace of g of t plus a. Okay, so we're going to do a couple of examples and see how we can use that. The first problem won't really require much of anything, but what I do want to show you is in the Laplace transform table, what we're working with is actually on the very last page. So I'm going to scroll, not so quickly to make you dizzy, but just to get us to that last page where we see all the shifting. Okay, so 54 was what we were dealing with before, the e to the at f of t. Laplace of that gives us a shift in the s world. Now we have the Laplace of u of t minus a gives us an exponential multiplier in the s world. And if we looked at the Laplace of f of t minus a, u of t minus a, it would give us e to the minus as, f of s. And then here's the one that I like to use. Laplace of g of t times u of t minus a gives us e to the minus as, Laplace of g of t plus a. Okay, so I want to hone in on 55 real quick, because 55 says that if you take the Laplace of u of t minus a, it gives you e to the minus as over s. Okay, so you just have to identify what a is, and then you can go from there. So let's go back to our problem. I can rewrite Laplace of 3 times u of t minus a as 3 times the Laplace of u of t minus a. And so this is just going to be 3e to the minus as over s based on our table. Okay, so no real work involved there. The next one requires a bit more work. So in this one, we have the Laplace of t plus a times u of t minus 3. And I'm going to show you 2 ways to do this. We're going to focus on using Laplace of g of t, u of t minus 3 equals e to the minus a, which is 3s, times the Laplace of g of t plus a first. And then in the other one, we'll focus on the other form where we look at the Laplace of f of t minus a, u of t minus a. I'm going to change those a's, sorry, to 3's, is equal to e to the minus 3s big F of s. Just so we can see, or you can see, which one you like more. All right, so I'm going to start with the first one. And I have g of t is equal to t plus 1. And I'm supposed to be going over here and saying, oh, well, I need g of t plus 3. And if I can get g of t plus 3, then I can write this all out for myself. So g of t plus 3, that means go back to g of t, and wherever there's a t, replace it with t plus 3. So this is t plus 3 plus 1, which is t plus 4. Okay, so that means that the Laplace of t plus 1, u of t minus 3, is equal to e to the minus 3s times the Laplace of t plus 4. Where we know how to take the Laplace of t plus 4, it's going to give us, we still have the e to the minus 3s, but then the Laplace of t is going to give us 1 over s squared, and the Laplace of 4 will give us 4 over s. And then we're done. Okay, so if we try it the other way, then we have that f of t is equal to we have f of t, sorry, that's not what I want to do. I need to rewrite t plus 1 so that it has a t minus 3 shift in it. So the way I do that is I write it as t minus 3 plus 1, which is going to give me t minus 3 and then a plus 4, where I'm kind of keeping that t minus 3 separated from the plus 4. Okay, so now I can say that I'm looking at the Laplace of t minus 3 plus 4, u of t minus 3, which, using the linearity property, this is equal to the Laplace of t minus 3, u of t minus 3, plus 4 Laplace of u of t minus 3. Okay, now using the definition above, it says that those u's give us an exponential multiplier. So this gives us e to the minus 3s. And then the Laplace of t minus 3, this one's kind of weird because we have to remember that there's a shift here. So it should just bring us to, like we've dealt with the shift. We have e to the minus 3s. And so then we'll just focus on taking the Laplace of t here. Okay, that's kind of weird. Plus 4 times, when we deal with the Laplace of u of t minus 3, that's going to give us e to the minus 3s over s. And that's from the table from before. Now we take the Laplace of t, which is 1 over s squared, and we get e to the minus 3s times 1 over s squared, and then plus the 4e to the minus 3s times 1 over s. And of course, we can rewrite that so it resembles the previous way we did it, to be e to the minus 3s times 1 over s squared plus 4 over s. So the difficulties, you may see them, are remembering that you need to rewrite the function so that you have that minus 3 plus 3, so you need to use the trick. Then you've got to use linearity. After linearity, this step is weird, where you go from Laplace of t minus 3, u of t minus 3, to the exponential multiplier, and then the Laplace of t without the shift at all. So you have to remember that part. And that's actually why I prefer the other way, because I don't have to remember quite as much. So in the next problem, I'm going to use my preferred method, but if you prefer the other way, by all means, do it. Okay. So in the next problem, we're looking at the Laplace of the quantity of 2t minus 3 times u of t minus 1. So here a is equal to 1, f of t is equal to 2t minus 3. So I want f of t plus 1 because I'm using my second form, so I need my f of t plus a. So everywhere there's a t, I put in a t plus 1. So I have 2 times t plus 1 minus 3, which is 2t plus 2 minus 3, or 2t minus 1. Okay? So the Laplace of 2t minus 3 times u of t minus 1 is equal to the e to the minus as, a is 1, so it's just e to the minus s, times the Laplace of 2t minus 1, where now the shifting has already happened. We don't have to remember anything at all. We just take a pure Laplace transform. This becomes e to the minus s times 2 over s squared minus 1 over s. And then we're done with that one. Okay. So this video is already at 40 minutes, and the next problems, the next examples I'm going to do are going to be dealing with the Laplace inverses and then some examples on how to handle this with differential equations. So I will finish with the inverse Laplace transform, but then I'll make a separate video for the differential equations. Okay? All right, inverse of the second translation theorem. If we take the Laplace inverse of e to the minus as, big F of s, it will equal little f of t minus a, u of t minus a. And so this is saying that if we see an exponential multiplier in the inverse Laplace, then we're going to expect a unit step function in the f of t world. It means we're still going to need a partial fraction decomposition when dealing with these. And we need to make sure that the exponential function is not actually part of the partial fraction decomposition. So this will be a good chance to review once again how to handle these partial fraction decompositions. We're going to deal with some of these separately. So I'll rewrite this as the Laplace of e to the minus 3s times 1 over s squared times s plus 1 times s minus 4. That way my eyes are focusing on the fraction without the exponential function. So big F of s is equal to the 1 over s squared times s plus 1 times s minus 4. I need to rewrite this so that I have all the different factors as possibilities for denominators in a sum of fractions. So s squared is just s showing up twice, so that gives me an a over s plus a b over s squared. The s plus 1 is linear, so I expect a constant c over s plus 1. And then the s minus 4 is linear, so I expect a d over s minus 4. Okay, then we multiply both sides by the LCD and clear. We get 1 is a s times s plus 1 times s minus 4 plus b times s plus 1 times s minus 4 plus cs squared times s minus 4 plus ds squared times s plus 1. Okay, now I'm going to use the trick where I let s take on values in order to solve for a, b, c, and d. So first I'm going to let s equal 0. When I do that, I get 1 is equal to, it looks like a times 0 plus b times 1 times minus 4 plus c times 0 plus d times 0. So I get 1 is minus 4b, and b is equal to a negative 1 over 4. Then I let s equal minus 1. So then 1 is equal to a times 0 plus b times 0 plus c times 1 times minus 5 plus d times 0. So this means 1 is equal to a negative 5c, so c is a negative 1 over 5. Then I let S equal 4. When S is 4, we get 1 is A times 0 plus B times 0 plus C times 0 plus D times 16 times 5. Sorry, that kind of got cut off at the edge there. So simplifying this, 1 is equal to 80D. So D is equal to 1 over 80. Okay. Now, another thing that we could do is we could, and this is going to be a little strange because in previous problems, when I didn't get all of the unknowns by using this process, I then multiplied everything out and I did equating coefficients. But I want to show you something else. Really my goal is to show you all the tricks of the trade so that you can get through this course. I can pick a less strategic S value that will allow me to get A. Okay. Letting S equal 0, negative 1, and 4 was nice because it helped me to get rid of 3 of the unknowns and solve for a 4th. But I have the 3 unknown values, so I can plug those in too. So let's see. I'm trying to think of what would be a nice number to use. Maybe 2. 2 looks not so bad. Somewhere in between -1 and 4. That's why I'm choosing 2. So I'm going to let S equal 2. There's a whole lot of arithmetic that shows up, but it's okay. So then I get 1 is equal to A times 2 times 3 times -2 plus B times 3 times -2 plus C times 4 times -2 plus D times 4 times 3. So I just plugged in 2 and simplified what it is, but now I'll do those multiplications out. Here I get 1 is 6 times -2 is -12A minus 6B minus 8C plus 12D. Now I know B, C, and D, so I plug them in. 1 is -12A minus 6 times the -1/4 minus 8 times the -1/5, and then plus 12 times a 1 over 80. Okay. And then rewriting this again, I have 1 is -12A plus 3/2 plus 8/5, and then plus, let's see, that'll become 6 over 40 and then 3 over 20. Okay, so finally what I have, I'm going to move the 12A to the left-hand side, and I'm going to subtract the 1 over. So 12A is -1 plus 3/2 plus 8/5 plus 3 over 20. And then I'm going to get my handy-dandy calculator that can simplify fractions. It's just a simple TI-30XS. I have a -1 plus 3/2 plus 8 over 5 plus 3 over 20. And that gives me 12A is 9 over 4, which means A is 9 over 48. And 9 divided by 48 simplifies to be 3 over 16. Okay, so we have all of our values. This was like the majority of the work for this problem. And so finally, we can go back up and remember what we were doing. We were just trying to rewrite a fraction. Okay, so what we have here is that we're actually dealing with the Laplace inverse of e to the -3s times, and then I'll rewrite it all. So I have 3 over 16 over s minus 1/4 over s squared minus 1/5 over s plus 1 plus 1 over 80 over s minus 4. Oops. Okay, so the e to the -3s just puts a u of t minus 3 on the outside, and then t has to go to t minus 3. So let's see how we can use some notation to help us with this. This is equal to the u of t minus 3 times, and then I have a 3 over 16, and then the Laplace inverse of 1 over s is 1, and then that's evaluated where t goes to t minus 3, which that's not going to change anything here, minus a quarter. The Laplace inverse of 1 over s squared is going to give us t, where t has to go to t minus 3, minus 1/5. The Laplace inverse of 1 over s plus 1 is e to the minus t, where again t has to go to t minus 3. And last is plus 1 over 80. The Laplace inverse of s minus 4 is e to the 4t, where t has to go to t minus 3. Okay, finally, last step, this is equal to the unit step function of t minus 3 times 3 over 16, no changes with the shift, minus 1/4 t shifts to t minus 3, minus 1/5 e to the minus, and then instead of t, in parentheses, I put t minus 3, plus 1 over 80 e to the 4, and then instead of t, in parentheses, I put in t minus 3. And then I'm done. So it's that last little bit, that last quick shift that you have to do that can be forgotten, very easily forgotten. So be very, very careful. Okay. All right. So that concludes the translation theorems. The shift on the s-axis, the shift on the t-axis, how to do the Laplaces of them, how to do the Laplace inverses of them. Make sure you're good on all of these, because already this is quite a bit. When we take all these new tools and apply them to differential equations, we should be at the point where we're comfortable with the shifts already. Okay, so I'm going to end this video now, and then I'll make a second video that goes over a couple of differential equations that include these shifts. And if you have any questions at all on any of the translation theorems, please feel free to reach out.